Today we are going to wrap up everything that we've been doing over the last 5 days with curve sketching, right? Graphing functions or finding information about the graphs of functions from its first and second derivatives. So over the last few lessons we've had a lot of information, and I thought maybe now would be a good time for us to put it all in one spot. So on our first slide you have this chart. If it's a little too small for you, you can go to the front of your notes packet, and if you flip it over, it's right here, and this is the one I'm going to be working with because I just can't write that small. So let's see if we can back this up a little bit, and I think that should do it. So again, this is on the back of your notes cover sheet, or you could certainly use the one that's in your notes, either one. So this is going to just tie a lot of information together for us. So when we talk about curve sketching and we talk about a lot of these connections, the first thing I'm going to do is I'm going to put up here and say this is for a continuous function f of x. Because if the graph is not continuous, then we've got a whole other slew of things that could be going on. So this chart is really just talking about continuous functions. Okay? All right. So here we go. When our function is increasing, right, we know it looks like this. I don't need to necessarily draw that, but our graph is going uphill. We know that the first derivative is positive or above the x-axis, however you prefer to write that. Or if you want to write both, that's okay. Sometimes I feel that the more we write, the more cluttered it's going to get. Okay. When our graph is decreasing, going downhill from left to right, our first derivative is negative, or we've said below the x-axis. Okay. All right. So if our graph has a relative max at x equals a, so the graph is going up and then it's going down, right? We all know what a maximum looks like. The first derivative is equal to 0. I'm going to come over here and put some notes in here in just a minute. The first derivative is equal to 0, but we also want to note that the first derivative changes from positive to negative, right? The graph is going up, then the graph is going down. So the slope is positive, then negative. Okay? If we have a relative minimum, right, going down, then going up, the slope is still 0, but the derivative changes from negative to positive. Okay? If our graph is, actually let's finish right here. If our graph, where's my pen here? If our graph has a relative max, I'm going to keep going in my chart here. My second derivative, this was that alternate form of the second derivative test. My graph is concave down, right? So my second derivative is negative. If it's a minimum at b, my graph is smiling or concave up, so my second derivative would be positive. Okay? All right. Here's the deal. The other option here, I should keep the same color. I just kind of left us a big spot for notes. If we have a max or a min, yes, our first derivative equals 0. That would be that smooth max or min. We also know f prime of x may not exist, meaning we have like a cusp or a corner, which would mean f double prime of x also does not exist, right? So this is kind of that another case. The big deal, I'm going to write most importantly in this whole column, the first derivative must change sign. Okay, you can even circle that. Okay. To have a max or a min, our first derivative must change signs. Okay, that's a big deal here, from positive to negative or negative to positive. All right, let's go down here. If our graph is concave up, we said it looks like a cup, it looks like it's smiling. We've said the second derivative is positive. But yesterday we also made the connection that the first derivative is increasing. So it's really up to you. Do you want to use the first derivative to find the concavity, or do you want to use the second? And it's going to be case by case. Okay. If our graph is concave down or looks like a frown, right? I could even write that in there. Our second derivative is negative or below the x-axis. And our first derivative would be decreasing. Okay? All right. If our graph has an inflection point at C, remember inflection point is when we change from concave up to concave down, then we know that f double prime of x changes sign. That's the most important thing, right? Finding those by setting the second derivative equal to 0 or asking where it does not exist. That's going to give us our candidates for inflection points. Okay, most importantly, I guess it doesn't matter, the second derivative changes sign. Okay, well, let's go back and fill in this box here. If we're changing concavity, that means our second derivative is changing sign, which means our first derivative is changing from increasing to decreasing or decreasing to increasing. Increasing turns into decreasing or vice versa. By the way, if a graph changes from increasing to decreasing or decreasing to increasing, that would mean we have a local or relative max or min on the first derivative, right? This is in the first derivative chart. Okay. So this is taking the last few days, kind of putting it all in one spot. Certainly you can notate this however you want. If you want to go in and just say a negative means below the x-axis, a positive means above the x-axis. I mean, that is completely up to you. Okay? All right, pause if you need to, but I'm going to go ahead and I'm going to go back to our notes and we're ready to move on to slide 2. All right. So, we would like to sketch a graph of f, which is a continuous, even, we'll come back to that word, function on the open interval -4 to 4 with the given properties in the table. Okay, let's talk about even for a moment. When we've talked about function symmetry, we've talked about even and odd, and even means symmetric over the y-axis. Right? Whatever we see over here, we'll see over here. All right, here we go. So they're giving us information about the original, the first derivative, and the second derivative at specific intervals or points of x. So when x is 0, the y value is -2. We can go plot that. Actually, let's go plot all the points, right? This is a point. This is a point. Let's go plot those points. So I have the point 1, 1, 2, 2, 3, 3. I'll come back to the symmetry at the very end. Okay. So I have 4 points right now. I don't know what the function is between 0 and 1, but I do know that the first derivative is positive, which means our graph is increasing, and the second derivative is negative, which means concave down. So I'm actually going to grab a pencil, because I may need to change something here in a little bit, but I want to be increasing and frowning. I'll come back to that transition in just a bit. So we just did that one. Let's do this one. I'll come back to these. Between 1 and 2, because I really want to know how to connect the points. Between 1 and 2, my first derivative is positive, and my second derivative is positive. So I want to be increasing concave up. That's, I know, kind of odd. Let's come back to that transition in a bit. Let's connect from x equals 2 to 3. I am still increasing, but now I'm back to concave down. And then after 3, so between 3 and 4, they want us to stop at 4, I am decreasing, concave down. Okay, so we've got a basic shape. Let's talk about what's happening at x equals 1. They're telling me the first derivative is 0. That means a smooth max, min, or shelf. Well, I'm not changing direction, so it looks like that needs to be a shelf, so I'm going to round that out. So let's come up and let's flatten that out. The slope has to be the 0 there. It's a tight squeeze, I know. At 2, the slope is 1, the second derivative is 0. The second derivative is 0 because we changed concavity. The slope of 1 just means, well, our spaghetti should kind of be slanted a little bit there. So we can come up and just change concavity. At 3, my slope is 0, so smooth, max, min, or shelf. Well, look at that. It's a maximum, isn't it? So just make it nice and smooth, which it was already. The only thing I felt like I needed to go in and clarify or clean up was that shelf at x equals 1. Well, now let's just go get our symmetry in here. So this point flips over, this point flips over, and this point flips over. But it's the same graph. And now when I look at this point here at x equals 0, now I understand why the first and second derivative did not exist. We have a bit of a cusp there, don't we? Okay. Good. All right, let's take a look at this third slide here. Shown below is the graph of f prime of x. We would like to determine when the graph of the original is increasing, decreasing, concave up, and concave down. And then, for which values of x will the function have a max, min, or inflection point? Okay, we are going to use our chart that we just made. And my camera froze again, so, oh, there we go. So if they gave me the graph of the first derivative, I'm going to get all of my information from right here. Okay? All right. So I would like to know, and I'm going to use some different colors here. I'd like to know when the original is increasing. And my original is increasing when the first derivative is positive or above the x-axis. I'm going to use orange for that. This is old stuff. So when my first derivative is positive, my original is increasing. So let's say from -3 to +2, and then how about from 7 to, let's say, infinity. I know I don't have arrows on the ends, but let's put them there. Okay. Likewise, the original is decreasing when the first derivative is negative. So I'll use green for that. Right? Here's my first derivative, and it is negative, well, everywhere else. So from what? -infinity to -3, and again from 2 to 7. Okay. While we're here, let's jump down and talk about maxes and mins. I'm grabbing my chart again. We said our graph will have a max when the first derivative changes from positive to negative. Well, let's take a look. My first derivative changes from negative to positive. That's a minimum. Here, I change from positive to negative, so that's going to be a maximum. And then at 7, I'm going from negative to positive, so that's going to be another minimum, isn't it? We, by the way, could also just kind of lightly sketch out our increasing and decreasing behavior to answer that question. Okay. All right. Well, let's finish by talking about the concavity. I want to know when the original is concave up by using the first derivative. So again, my graph is concave up when my first derivative is increasing. I'm going to jot that down. F prime is increasing. And I will use like a lavender color for that. So this is my first derivative. It is increasing here. And it is increasing again here. So let's say from negative infinity to, I don't know, let's call that -1, estimating. And then from, let's call that 5 to infinity. So when my first derivative is increasing, my original is concave up. And then I'll use this like magenta color. My original is concave down when my first derivative is decreasing. And my first derivative is decreasing from -1 to 5. My inflection point occurs when the first derivative changes from increasing to decreasing, or vice versa, or when it has a relative max or min. Right, so here's my first derivative. There's a max, there's a min. And so that's going to happen again where I'm changing concavity, which is at -1, and x equals 5. That looked like it said 7. So x equals -1, x equals 5, where f prime has a max or a min. Okay. All right. Let's take a look at this last one. Same kind of idea. Here, I'm saying f is continuous on the closed interval 0 to 5, and f of 0 equals 0. Sketch the graph of f whose first derivative is shown below. Right, so I'm giving you the first derivative. I'm asking about the original. Same thing. I'm giving you the first derivative, and I'm asking about the original. So let's use, I'm going to use the same colors. My original is increasing when my first derivative is positive. Okay, increasing. My original is decreasing when my first derivative is negative. So we could write it out much like we did on the last one, or we could just go ahead and put it in our graph. First of all, f of 0 is 0. Okay. I want to be increasing until I get to 1, decreasing from 1 to 2. I don't know how steep to make this. Okay. Increasing from 2 to 3, decreasing from 3 to 5. Again, I don't know how steep. I'm just going to lightly with my pencil put in my appropriate increasing and decreasing behavior. Okay, we could write that down if you wanted to. We are increasing from 0 to 1, and then again from 2 to 3, decreasing from 1 to 2, and then again from 3 to 5. Okay. Let's do the same thing with the concavity. I use light purple for concave up. I am concave up when my first derivative is increasing. This is the first derivative, and it looks like it's only increasing from 4 to 5. Okay. I am concave down when my first derivative is decreasing, which is everywhere else, right? Concave down from 0 to 2 and from 2 to 4. Okay, so we've got our appropriate increasing and decreasing behavior. Now I'm just going to go and put in that concavity. Let's start here at 0. I'm concave down from 0 to 2. So I want to increase and frown and decrease and frown. Again, I don't actually know how high up or down to go. That's okay. I am still concave down from 2 to 4. So I'm going to increase and decrease, but I am still frowning. Let's come back to this. If I decrease and then increase, but I'm still concave down, it creates a cusp here, doesn't it? That actually works out because look, my first derivative does not exist at x equals 2, which means I have a problem in my original at x equals 2. It fell into place, didn't it? It just happened that way. This max and this max are nice and smooth because look, the first derivative was equal to 0 there, so they're nice and smooth transitions. All right, from 4 to 5, I am concave up, and I can see I need to be decreasing, so I'm going to make it look like a smile or like a cup, but go downhill. And that's our graph.